We're going to graph exponential functions with the base a. This is 12.2a. We've got 3 previous videos for chapter 12 that are linked in this description if you need them. In exponential notation, n to the x is the exponent, and it tells us how many times the base is used as a factor. So now let's talk about irrational exponents such as 2 to the pi. The number pi is an unending decimal representation. It's a non-terminating decimal. And each of these are an approximation to pi. And the more decimal places we include, the better our approximation will be. The more accurate our approximation will be. So if you consider this sequence, each of the numbers in this sequence is already defined, and the exponent being rational. We can make a fraction out of them, couldn't we? And these numbers get closer and closer to some real number, and we define that number to be 2 to the pi. We can define exponential notation for any irrational exponent in a similar way. So any exponential expression, a to the x, and a is greater than 0, now has meaning whether the exponent is rational or irrational. So I have a definition for you. Exponential functions are defined using exponential notation. And the function f of x equals a to the x. That's where the a is some positive real number constant. It's different from 1. It's called the exponential function, base a. Now if you notice, we exclude the case where a equals 1. When a equals 1, the function of x equals a to the x. It's 1 to the x. So it equals 1. No matter how much we multiply 1 to itself, it's still going to be 1, right? So that's for all x, which is just a horizontal line. 1 to the second power, third power, fourth power, it's still going to be a 1. So here's some examples. And notice that the variable is the exponent. In every single one of these functions, it's an exponential function because the variable is the exponent. See that? And these are not exponential functions. The variable is not the exponent. So for it to be an exponential function, the variable needs to be the exponent, like here, okay? All right. The most commonly used exponential functions are f of x equals 2 to the x, 10 to the x, e to the x. And these functions are usually found on scientific calculators. Now, we briefly discussed e in a previous video, and we're going to go into detail more in 12.8. All right? We can graph y equals 2 to the x. We use the graph to approximate 2 to the square root of 2 as an exponent. We make a table to find some solutions and plot them, then draw the graph. So if y equals 2 to the x, well, if it's 2 to the first power, it's going to equal a 2. We make our table of values. If it's 2 to the second power, it's going to be a 4. If it's 2 to the third power, it's going to be an 8. And if it's 2 to the half, that's a negative 1, isn't it? When we have a fraction exponent, it's a negative. So 2 to the 1/4 power would be a negative 2. We'd have a, see that? Negative 3. 2 to the 0 power equals 1. Anything to the 0 power exponent is a 1. And as x increases, the function value increases. And as x decreases, the function value decreases towards 0. So this ends up being our graphed line. Look at this. We have this nice curve, and we graphed and plotted our points, and that's what we got. So to approximate 2 to the square root of 2 as an exponent, we find square root of 2 on the x-axis at about 1.4. It's about right here, almost at 1.5. And we find the corresponding function value at 2.7, approximately. It's almost at 3, so it's right there. See that? And we can make comparisons between functions using transformations. We can graph y equals 4 to the x power. We could plot some points and connect them. Now, 4 to the x is the same thing as 2 squared to the x. So it's also 2 to the 2x power. See that? And comparing this to that y equals 2x that we just did from the previous example, y equals 4 to the x nears the y-axis more rapidly than the graph of y equals 2 to the x. It's closer to the y-axis when it's going up, and the graph of 2 to the 2x power is a shrinking of y equals 2 to the x. And knowing this information allows us to graph y equals 2 to the 2x right away. Each point in the graph of 2 to the x is moved half the distance to the y-axis. So if you take a look at this, here was our original graph in the pink, and in the blue is what's happening at half the distance coming up here. See how it's closer to the y-axis when it comes up? And if you look at the plotted points, for our previous example, we had 3 and 8, but now we have 1.5 and 8. See how it's half? So it's shrinking. This was a 2 for our x, now it's a 1, it's half. This was a 1, now it's a 0.5, it's half. See that? And we can graph y equals half to the x power. We can plot some points and connect them, but keep in mind that it's the same thing as 2 to the inverse of x. If we compare this with our first example, y equals 2 to the x power, the graph of y equals 2 to the inverse of x is a reflection across the y-axis of the graph of y equals 2 to the x. Knowing this allows us to graph it. So this was our original pink one from the first equation, from the first example, and this is going to be what's happening as the reflection. We had 3 for our x value and then an 8 for our y right here. We get a -3 and an 8. So it's a reflection across that y-axis. See that? So, did you know that the square and the square root on a calculator are inverses? If you hit the square root's radical sign, then put in 25, and then hit that x squared button and equal, you'll be back at 25. If you just hit this radical sign and put in 25 and equals, you're going to get a 5. But if you hit this x squared button, it'll be back at 25. They're inverses, okay? And remember, for it to be an exponential function, the variable needs to be the exponent. We need to have the exponent up there as the variable, okay? Our next video is going to be 12.2b, and we're going to graph logarithmic functions. There's going to be links to those 3 previous videos and any other videos that I think might correlate with this one to help you out. And a link to that Algebra II playlist that I'm going to add this one to. Okay? So that's how we graph exponential functions, and that's how we know they're exponential functions. They have exponents that are variables, right? Keep going. I'm proud of you, and I'll see you next video. Bye.